Well, welcome back to your favorite pre-calculus class. Let's look at functions today. We'll start out with a little bit of vocabulary. Our domain is the set of all typically x values, but your input values. That's your domain. The range is a set of all y values, or typically y values. Those are your output values, set of all output. Um, and remember, there's no division by zero. Can't take square roots of negative numbers. At least right now, we're only working in the real numbers right now. And we're going to talk about what is or is not a function. So you can have a relationship between anything, right, in mathematics, but every relation is not necessarily a function. A function means for every input, there's only one output. For every input, there's only one output. For every x, there's only one y. That's what I want you to remember. And so there's different ways to look at this. This is a set of ordered pairs, this relation, right? So you've got all these x's and y's. And notice, and I'm going to go ahead and do it this way with my x's and my y's. Notice my 1 input outputs a 2. And then my 3 outputs a 7, right? 3 is paired with 7. 3 is the x, 7 is the y. The 2 outputs a 9, and then the 8 outputs 11. And so how I do this is I say, well, for every x is there only one y, so for this x there's one y, right? Then I go to the next one. I say for this x, for an x of 3, there's only one y, right? So that one's okay. For this x, for the 2, looks like it only has one y. So far, so good. And finally, for every x, there's only one y there. So is this a function? I say yes, this is a function because for every x, there's only one y for each of those. Let's try it for this next set of ordered pairs here. And by the way, my domain on this last one, my domain is the set of all x values. So it would be that 1, 3, I guess I could put in order. 1, 2, 3, and 8 are all my x values. My range is all those y values. 2, 7, 9, and 11. Oops, that's a really bad braces there. So let's look at this next one here. I have a -3 is mapped onto 4, right? That's my x, y first one. So for that x, there's one y. 5 goes to 6. For the 5x, there's one y. For the 7 input, there's one output. 4. For the -2 input, there's one output. 3. Oh, I'm sorry. I should have listed that 7 also goes to 4. Whoops. I don't need to list the 4 twice, but the 7 goes to the 4 right there, right? So again, let's check it. Is this thing a function? Well, for this x, there's one y, right? For the -3 has one output. For this x, oops, the 5, for that x, it has one y, the 6. So far, so good. For this x, the 7, it outputs one y. I know it's the same y as the -3, but each of those x's has its own y, right? For every x, there's only one y. So it's okay. And then that -2 has there's one y for that -2. So is this a function? Yes, it is. This is also a function. Let's do the next mapping. I've mapped the first two set of ordered pairs, -2, 4, -1, 6, and then 0 goes to 3. And then notice I have another -2. -2 also goes to 8. So now let's check, is this a function? Well, for this x, that -2, how many y's do I have? Yeah, there's not just one y. This x has two y's. So for every x, there can only be one y. So this is not, right away it failed. This is not a function, okay? And let me give you a visual test for this. There is a visual test for this. This is called the vertical line test. So I wanted to introduce it as a mapping initially, but you guys know that you could you could graph these ordered pairs. Like, for example, let's graph this second one here. We have -3, 4, I have 5, 6, I have 7, 4, and I have -2, 3. If I graph them, the vertical line test says, well, let me run it through every input, and the vertical line can only hit one time wherever it's defined. So I run it through for -3. I only hit one time. That means for that input, there's only one output. I can only hit once. I hit once again. I can only hit once. I hit once again. I can only hit once. So yeah, visually this was a function. Let's look at the one that failed though. This -2, 4, -1, 6, 0, 3, but then -2 also hits at 8. So notice when I tested at -2, see how I hit twice on that one? So it fails the vertical line test. If I was to graph these, I can only hit one time. It's testing it visually. For every input, there's only one output. Now, without mapping or without graphing, is this last one a function or not? Yeah, hopefully you notice that this one, without even mapping it, see that 5. Oh, I'm sorry, that 5 goes to 3. Well, actually, let's look at this. 5 to 3. That's the same point. I know it's listed twice, but that is not a problem. And then 9, 10. See how I pass? I pass. There, yes, it's the same dot, but it doesn't matter. It's the same dot, right? It's still one input, one output. So in all actuality, even though it's the same point, yes, this is a function. Now, if we would have had like 5, 2, now that's different. Now I have a couple different y values for an input of 5. That would be different. Now let's look at some graphs. Now this is an infinite amount of ordered pairs, right? Because it's got this solid graph line. Looks like we've got some sort of exponential curve here in blue. If I run a vertical line test through it, I'm only hitting once. Wherever I test it, do you notice that you're only hitting once on that graph? So this, yes, is a function. That'll be fine. Is the second one a function? No, yeah. See how we're going to hit twice? Anytime you hit twice, it's just going to fail it, right? Even though you only hit once over here, it doesn't matter because anywhere else you test it, you're hitting twice, right? So not a function. Not a function. How about the third one? Yeah, hopefully you see you're only hitting once. I know it's pretty steep, but you're still, even where you can test that, it is going up and to the right. You're only hitting once. All these spots you're testing, you're only hitting once. So that, yes, is a function as well. So the next example, so we've looked at ordered pairs, graphing, right, mapping them, or you can plot the points and look at them. We looked at some graphs. It's got to pass the vertical line test. How about if they just give you a function now, algebraically? X squared plus 3y squared equals 7. How are you going to know? Well, what I would do, instead of like going to the effort, trying to graph all this right now, I would just solve for y and see intuitively what's going to happen here. So I've got 7 minus x squared. I'm going to divide both sides by 3. So I've got y squared equals 7 minus x squared all over 3. Now when I solve this for y, I've got to square root both sides. Well, if I square root both sides, don't forget that you have to do what? You got to throw on a plus minus on that, right? It's kind of like if you were solving x squared equals 9. If you square root both sides when you have x squared equals 9, then it's popping out 2 solutions because 3 squared is 9, but so is -3 squared. Both of those satisfy the original, right? So if you're square rooting both sides, you got to throw on that plus minus. Because technically speaking, that's an absolute value on that, square root of x squared. Okay, so don't forget that's throwing on a plus minus when you do that. So let's think about it for a minute. If I throw in, like let's say we throw in like 1 for x, right? I throw a 1 in for x. So I've got 7 minus 1 squared. Right, I'm testing this input here. So I got 7 minus 1, I got 6 over 3, I got 2. Plus or minus the square root of 2. I have two values. I have the square root of 2 and I have the negative root 2. Both of them for an input of 1. So for that input, 1, I have two outputs. I have a plus and a minus y for that. Are you following me? So is this a function? And hopefully you say, no, it's not. It's not a function because I got a plus minus. I got two outputs for my y every time I throw an input in. So this is not a function, not a function. So generally speaking, well, actually, let's do one more and then we'll talk about this generally. Let's solve this next one. X squared plus y to the fifth equals 1. We're going to do the same thing. We're going to solve for y. And now we're going to fifth root this, the fifth root. So y equals the fifth root. Now, do I have to slap on a plus minus? No, you don't, because like, for example, x cubed equals 8. If I third root that, right, there's only 2 will satisfy, only 2 cubed equals 8, right? Negative 2 cubed is not 8. Negative 2 cubed is negative 8, right? So you don't throw on a plus minus when you take an odd root. It just stays the fifth root, not a plus minus there, right? So if I throw one input in, it's going to spit out one output for my y. Again, there's no plus minus there, right? Because I took an odd root. So is this a function? Yes, this is a function. So let's generalize this. How do I know if I'm going to end up with a plus minus when I solve for y? The y, if the y is to an even power, it will not be a function. If the y is to an even power, it will not be a function. If the y is to an odd power, you're going to be fine. It'll be a function. Okay. All right, so function notation, f of x. F of x, this is just a nickname for y. But what it's saying is it's saying, go ahead and input that x value and see what you get for y, right? So if f of x equals 7, it says find the following. So first let's find f of 3. So if I use this function notation, this f of 3, what this means is find y, or f of x, in other words, find y when x is 3. Okay, oops, I'm not doing that. I have f of x equals, 2x minus 5. I copied this wrong. I have f of x equals 2x minus 5. Find the y value. Find the f of x. And your x is 3. So we're going to go ahead and put the 3 in for the x. So f of 3 equals 6 minus 5. F of 3 equals 1. My input was 3. My output, my y, was 1. So it's giving me that point. I inputted 3, it outputted 1. 3 comma 1, right? That's what the instructions. Again, mathematicians are lazy. If they can shorthand the notation, they will. That's why they use function notation. Not lazy in the sense they don't want to work, lazy in the sense they want it shortened, right? Very precise, concise. And function notation really helps us when we get into calculus. So instead of saying find y when x is 3, they'll just say find f of 3. Right? They want you to use the function notation. Now the second part of this says solve f of x equals 7. All right, well, f of x is 2x minus 5. And they're telling us f of x, remember f of x is y, they're telling us that y is 7. The whole y is 7. So solve that. What x value spits us out that 7? Right? So I replaced f of x with the 7. So we just solve it. 12 equals 2x. I'm going to go ahead and divide both sides by that 2. And it looks like x ends up being 6. Right? So 6 is solving that, provides us with an output of 7, a y value of 7. Now some more function notation. So we have this f of x equals 2x minus 5. And this second part B here says find f of x plus 3. So this time x plus 3 is going in for x. X plus 3 is going in for x, right? That's my input, is that x plus 3 now. So f of x plus 3 ends up being, let's go ahead and solve this, 2x plus, or simplify this, 2x plus 6 minus 5, so we got 2x plus 1. So f of x plus 3 ends up being 2x plus 1. Some more function notation. What is f of x? F of x plus f of 3. Well, remember, f of x is 2x minus 5. So f of x, let's replace it. What is it? It's 2x minus 5 plus, and what was f of 3? Remember, we did f of 3 already, right? We plugged the 3 in, and we got 2 times 3 minus 5, and we ended up with f of 3 was 6 minus 5, or 1, right? F of 3 is 1. So what is f of 3? F of 3 is 1. So that's saying take your f of x function, 2x minus 5, and add it to whatever you got for f of 3, which was 1, right? So what is 2x minus 5 plus 1? Well, it's 2x minus 4 when I combine those like terms, right? F of x plus h. Remember, f of x was 2x minus 5. So f of, now it's inputting x plus h in for that x. X plus h is now our input. So we're going to go ahead and distribute that. So it looks like f of x plus h, again, x plus h becomes the input for x, right? All right, remember we got f of x is 2x minus 5. This time it says plug in negative x. So we got 2 times negative x, or negative 1x, right? So 2 times negative 1 is a negative 2x minus 5. That's what f of negative x is. This next one we got f of x, 2x minus 5. This time they want us to find negative f of x. Negative f of x. So they're putting a negative in front of the f of x. Well, if I put a negative in front of the f of x, it's got to be distributed through to both of those terms because I got 2 terms there. So you see how this time we put a negative in front of that expression there on the right hand side? So negative f of x just ends up being negative 2x plus 5. All right, this would be a good you try problem. I would go ahead and pause the video and try each of these. All right, let's go ahead and check your first 2 problems there. The f of 5, you plug that in, should got 1/7 on that. F of x plus h, when you plug that x plus h, goes in for the x, right? You see it in red there. And that's as far as we can go once we distribute the 2 on the in the denominator there. And then finally down below here we've got f of x plus f of 5. Well, our f of x was x minus 4 over 2x minus 3. Our f of 5 we got in the first part. I think that was 1/7. Remember right? So we've got x plus 4 over 2x minus 3 plus the 1/7. Ideally, we do get a common denominator here, so we can combine these. So I'm going to give this a 2x minus 3, 2x minus 3. Both of them now have a 2x minus 3. This one over here, though, is missing a 7. So here we would have 7x minus 28 over this 7 times 2x minus 3. And then over here we've got 2x minus 3. I distribute the 1 there. 7 times 2x minus 3. So now they have a common denominator. So I have 7x minus 28 plus 2x minus 3. This is all over that common denominator of 7 times 2x minus 3. Combine any like terms. See the 7x and the 2x gives us the 9x. Negative 28 minus 3 gives me the minus 31. And this is over our common denominator. And that's as far as we can go on that one. These are also good little you try problems. You want to try these first. Pause the video. Be great. There's that one when you throw in the negative x. And then ideally what I would do, I see a negative x on the top and a negative 2x on the bottom. I would actually take a negative out of each of those. Factor a negative out. See how you got negative over a negative becomes a positive, so that'll cancel that. So you just end up with x plus 4 over 2x plus 3. I think that's your preferred form on that. Not that the other one's incorrect, but ideally take a negative out of both of those sets of terms. And then this last one we've got, when we're checking this one, you're just throwing a negative in front of that f of x is what they want. Right? So the negative in front of the x minus 4 over 2x minus 3. And so that negative f of x, and that negative, by the way, that'll pertain, go ahead and have it, I'll go ahead and distribute that to the top there, and then you leave the bottom alone, right? It's kind of like negative 1/3 is also written as negative 1/3, right? Or 1 over negative 3, but we prefer to write as negative 1/3. Let's take a look at this function notation with our graphs. The first one says, given the graph, notice we don't have an equation for it this time. Let's evaluate f of 3. So remember, this is saying find y, f of x, find y, when x is 3. That's what it means, right? F of 3, find f of 3. Well, when x is 3, here's my x value, that's 3 right there. When I input 3 onto the graph, what does it output? When I find my x on the graph, whoops, this is moving all over the place on me here. When I plug in a 3 for my x, and I find it on my graph, right, it's outputting, what's the value there? 1. It's spitting out a y value of 1. So f of 3 equals 1, right? This is the point 3 comma 1 right there. F of 3 equals 1. Now the second part says solve f of x equals 4, right? Solve this. Well, what f of x is a nickname for who? Y. This is like y is 4. Well, when y is 4, let's find where y is 4 at. Where is y 4 on the graph? Yeah, right there. Good. When x is 4, and where else? When x is 0. So at 0 I have a y value of 4. At 4 I have a y value of 4. Both of those locations I have a y value that's 4. So solve f of x equals 4. This happens when x is 0 and when x is 4. That's when f of x equals 4. That's when our y value is 4. Now let's go ahead and look at domains algebraically. Find your y values. I'm sorry, find your domain, a set of x values. When I'm thinking about domains and I'm given a function, what I'm thinking is, do I have any restrictions? Is there anything that x cannot be? So I have this y equals 2x minus 5. Can I throw a 1 in? Sure. And it'll spit a y value out, right? Could I throw 2 in, 3 in, 4 in? I can throw any x value in that I want, and it's going to spit out a y value, right? So my domain has no restrictions. So the domain of this y equals 2x minus 5, the domain, if I want to put it in set notation, is x such that x can be any real number. Element, this is element of all real numbers. That's my domain. I have no restrictions on this. Now we're going to use what's called interval notation for our domain. So we're just going to say it's got no restrictions. It goes from negative infinity to positive infinity, and that's how we're going to say that with interval notation. Again, this is set notation. Good to practice that. This is our interval notation. No restrictions. It runs from negative infinity to positive infinity. This next one we've got y equals 5x squared minus 3. Again, you're thinking to yourself, do I have any restrictions, or can I throw in any x value, any number that I want, and will it spit out a y value for me? Yeah, I could throw in positives, negatives, 0. It doesn't matter. It'll spit out a y value, right? So this again has no restrictions. My domain is the set of all x such that x is an element of the real numbers, or negative infinity to positive infinity, all real numbers. Whereas this bottom one, we do have a restriction. Remember, we cannot divide by what number? 0. Yeah, we can't divide by 0. What causes this denominator to be 0, right? That's going to be our restriction here. So I'm thinking, well, I cannot divide by 0, so when am I going to have a problem? When does 2x minus 5 equal 0? Well, let me add 5 to both sides and divide by 2 on both sides. Oh, it's 5 halves. 5 halves is going to be our problem child. X cannot be 5 halves because the denominator will become 0 if it is, right? Other than that, x can be anything we want. So my domain on this with interval notation would be, I'd say, well, x is all reals, but it cannot be that 5 halves. In interval notation, I say, well, it's coming from negative infinity up until 5 halves, but it cannot be the 5 halves. That's why I have a parentheses on that. That means it does not touch it. It does not touch the 5 halves again, but it keeps going. There's our domain in interval notation. The next one has a square root. Do I have restrictions on square roots? Can I take the square root of anything? Like, what's the square root of 0? Yeah, square root of 0, 0. Square root of 1, 1. Square root of 4, 2. Square root of 16, 4, and so on. What about negatives? Can I take the square root of a negative? No, right. I cannot. So my radicand, stuff underneath a radical, that stuff has got to be 0 or bigger. That's my restriction here. So if I add 5 to both sides, this will give me my domain. Divide by 2 on both sides. So I'm greater than or equal to 5 halves. So that's my domain here. X such that I can be, I can be any x value greater than or equal to 5 halves. But I've got to be numbers 5 halves or bigger. So my interval notation starts off at, see how I include it with a bracket? I start off at 5 halves and I shoot to infinity. Right? In fact, you could check it. I can't be anything below 5 halves, right? So 5 halves is 2.5. What if I plugged in 2? If I plug 2 in for x, I got square root of 2 times 2 minus 5. Oops, minus 5. I got 4 minus 5. Square root of -1. No, that's not a real number, right? We're not working in imaginary numbers here. So that's why it's not part of our domain. Yeah, can't take the square root of the negative here. Only real numbers. So similarly, that's going to be your trick. If you want to pause the video and try finding your domain on these last two, that'd be great. Hopefully when you're finding the domain on this one, you notice you get that radicand 7 minus 6. So the stuff under the radical has got to be 0 or bigger, greater than or equal to 0. Solve that. So you got negative x greater than or equal to negative 7. Now you got to get rid of this negative 1 out front. So don't forget that when you divide by negative 1 both sides, that's going to flip the sense of the inequality, that's called. When you flip that, that's called the sense of the inequality. So negative 7 over negative 1 is a positive 7 there. So I got to be less than or equal to 7. That's my domain on this. X such that x is less than or equal to 7. Less than or equal to. So I'm coming from negative infinity up until 7, and yes, I am including that, right? So anything 7 or below is going to be fine. If I go above 7, I'm going to have issues. So, like, let's say I tested 8. Is 8 in my domain? Should have an answer, no, I do not. If I replace x with 8, see how I get square root of negative 1? Again, that's not in the real numbers, right? It's not going to be on my graph. We're not working with complex numbers right now. Let's look at this next one. You've also got a radical. And by the way, the next one, the numerator has no issues. I can let x be anything up there, right? No issues there. But I do have a square root, so a square root's got restrictions, and it's in my denominator. So I'm going to take this radicand, I'm saying, okay, the 2x minus 5 is going to be what? Normally I'd say greater than or equal to 0, but remember it's in the denominator. I got to be greater than 0 because I can't divide by 0. That can't be equal to 0. It can only be greater than 0, right? Because the radical's in the denominator. I'm going to go ahead and add 5 to both sides. Divide by 2, which is a positive number, so the sense of the inequality stays the same. There's my domain, x such that, boy, my braces are struggling here. I'm greater than 5 halves on anything greater than, so parentheses, not including 5 halves. That's why it's a parentheses, not a bracket there. Not including 5 halves and on to infinity. Well, thanks so much for watching. We'll see you next time.